It's that time. We got to review for our first exam. So, remember at the very beginning of the course, we touched on some ideas from towards the end of Calculus 1. So, of course, you got to remember how to take derivatives, but then, of course, going backwards, we're covering these original functions, these integrals, okay, finding antiderivatives. And then we touched on the nicest theorem that we have here that allows us to relate derivatives and integrals, the fundamental theorem of calculus. Then we got to our very first technique of integration, use substitution. Okay, that's going to be our very basic technique, and then we'll learn actually more in the next chapter for the next exam. Then we got a bunch of applications from geometry and from physics. So in this series of exam 1 review videos, we're going to go ahead and do some more exercises from some of those previous topics. Okay, these won't be as in-depth as the previous ones, so if you need a refresher on that specific idea, please go back and rewatch the video from that particular section. So we're going to go ahead and start by reviewing use substitution. It is our very first basic technique of integration, and it is based on the chain rule. The idea is that I want to turn a hard problem into an easy problem. Let's go ahead and take a look here at this very first integral that we have. We want to look at the integral of x cubed over the square root of 1 plus x squared dx. All right, so doesn't look like anything that we've seen before. We don't have a nice antiderivative formula for this one, but we can actually go ahead and think about this using the chain rule in reverse. That's the use substitution rule, this change of variables. Now, we'll actually learn a different technique in chapter 3 how to tackle integrals of this type, but this is one way of attacking it. So what we're going to notice here is that I have a fraction and I have a square root in there. The rule of thumb, the kind of heuristic for use substitution is look either in the denominator of your fraction or perhaps even inside a square root. Okay, we want to look for compositions. And that's what we have here. So we're going to go ahead and set u equal to 1 plus x squared. Okay, so we have our change of variable. Now we need this differential du, this small change in u. So we take the derivative of both sides. Du is equal to 2x dx. All right. But I don't have this extra factor of 2, so I'm going to go ahead and play for the match, okay? So by shuffling some things over, okay, by moving that scale factor over, I get 1/2 du is equal to x dx. All right, but it doesn't look like I'm really done yet. And this is an idea. If we write this x cubed as x times x squared, I think I'm in business here because there's an x there and there's an x squared built into there. But how do I handle the x squared? Well, we go ahead and look back at original substitution, and I can solve that for x squared. So we note that x squared is equal to u minus 1. I can still come across the same results here. Just take a derivative on both sides, we get the same thing. But now I have everything that I need, x and x squared. So let's go ahead and rewrite our integral here. So I'll write the original one here, x cubed over the square root of 1 plus x squared dx. Okay, and now we go from the x world into the u world. So here we go. X cubed was x times x squared. The x squared is u minus 1. Okay, the x dx will combine. So if we notice there, x and x squared, we have x dx. X dx form our du earmuffs, okay? So x dx are our du earmuffs, that's 1/2 du. So we'll pull actually, let's just go ahead and write the 1/2 there. And then u minus 1 over the square root of u du. All right, let's go ahead and shove that 1/2 outside of the integral. Okay, it's a scale multiplier, so we can just go ahead and pull out the scalar. Now I have the integral of u minus 1 over the square root of u du. Now let's remember our exponent rules, okay? And our fraction rules as well, okay? We have stuff over a common denominator, I can just separate. So this is half of the integral of u over the square root of u, let's fix that, minus 1 over the square root of u du. Okay, and now we're just going to go ahead and use some exponent rules here, okay? U over the square root of u, well, square root of u is u to the 1/2, okay? And then how do we divide with exponents? We subtract the powers. So this gives us 1/2 times the integral of u to the 1/2, we'll just write it like that for the moment, then minus u to the minus 1/2 du. All right, we're looking good so far. Okay, now what do we do? Power rule. It's just our power rule. So 1/2 of, Well, power rule, we add 1 to the exponent and divide by the new exponent. So u to the 1/2 plus 1. So 1/2 plus 1 is 3 over 2. And then I'm going to do this off to the side here just so that we see. So you could start out by writing this u to the 3/2 over 3/2. But I really don't like this kind of fraction over fraction kind of thing. And so what are we going to do? How do we divide fractions? All right. Keep, change, flip. That's the action. Okay. And everyone knows that's how we divide fractions. So we're going to multiply by the reciprocal. 2/3, u to the 3/2. Okay. And I'm going to do a similar one for the next one here. So instead of dividing by 3 over 2, I'm going to multiply by 2/3. And then I'll have minus, right, u to the 1/2 minus u to the negative 1/2 plus 1. Well, negative 1/2 plus 1, that's a plus 1/2. Okay, and they're going to divide by a half, which is the same as multiplying by 2. Introduce our constant of integration. I'll go ahead and multiply through. And then I'm going to replace our u with x, okay? Everything was in terms of x. We got to end in x here. So 1/2 times 2/3, that's a third. U is 1 plus x squared. Okay, to the 3 over 2. And then minus 2 times a half, that's 1. And then I have square root of u there, which is square root of 1 plus x squared plus a constant. And we're done. We took a hard problem, turned it into an easy problem. Okay, now let's go ahead and look at an example of a definite integral where we need to use u substitution. We're looking at the integral from 0 to pi over 4 of e to the cosine square x times sine x times cosine x dx. Looks a little intimidating, looks a little scary, okay? But remember, we want to look for compositions, okay? Well, I see an exponential. Let's look at that exponent there. Cosine square of x. Okay, that probably seems useful. Okay, but that sine x cosine x probably looks a little useful too. We'll think about that in a second. Do you think we should do u equals cosine x? Well, that's a possibility. That is a way of looking at it. But then the resulting integral, we don't really have the tools to handle that just yet. It doesn't really look as easy. So a way you can do this, you can actually, you can do this in 2 substitutions. But we're going to go ahead and tackle it in 1 substitution here. So in dark blue here, I'm going to do u equals cosine square of x, not just cosine x here, okay? Now let's have a look here. Du is, well, let's take the derivative. We got chain rule, okay? That's our symbol for the chain rule, right? Okay, the chain rule. So something squared, I know the derivative of something squared is 2 times the something. So 2 cosine x times the derivative of the inside. And the derivative of cosine of x is negative sine of x. And then we have our dx there for our differential. Okay, well, think about our du earmuffs here, all right? Think about our du earmuffs here. I have sine x, cosine x, got a dx there. I want to link those two together. So we play for the match. Minus 1/2 du equals sine x, cosine of x, dx. Jolly good, there we go. All right, so we are ready to plug in. Not yet. Because remember, we are in the x world and I'm trying to go to the u world. So those limits of integration there, they don't hold anymore. They are not valid. Okay, there we go. So how do we handle this? What we're going to do is we're going to find our new limits of integration. There we go. So when x is equal to 0, come on, erase. Erase, please. So we're trying to find new u's here. So when x is equal to 0, we're going to plug in those x values into our substitution. U is equal to, well, cosine square of 0. All right, cosine of 0 is 1, and 1 squared is 1. And when x is equal to pi over 4, well, the corresponding u here, cosine square of pi over 4, well, let's see. Cosine of pi over 4, if we think about it using the hand trick or just look at a unit circle, square root of 2 over 2, and then we square it out, we get 2 over 4, which is a half. All right, so now let's go ahead and put everything in there. So our integral becomes, okay, we're going to integrate now from 1 to 1/2, okay, e to the cosine square x, that's e to the u, and then sine x cosine x dx, that's minus 1/2 du. So I'll go ahead and put the minus 1/2 out there. And this is an easy antiderivative. What function is its own antiderivative? E to the x, the exponential, okay? So we have minus 1/2 times e to the u, evaluated between 1/2 and 1. All right. And now we just go ahead and plug in top minus bottom. So e to the 1/2 there on the inside minus e to the 1, which is e. And a nice way I could write this here is minus 1/2 times the square root of e, that's e to the 1/2, minus e. Excellent. Good work. Okay, nice. Now, I want to make a quick remark here. Okay, you see this minus sign outside the integral, okay, and our limits of integration aren't in the natural order, and we're not going from small to big, we're going from big to small. You can if you want to, okay, if you wanted to, okay, you can reverse the order of integration back and write this as the integral from 1/2 to 1 of e to the u du, okay? Because if you reverse the order of integration, it costs you a minus sign in or out. Okay, you don't have to necessarily go through that step, just something to keep in mind here. Also, keep in mind here that I didn't have to go back into the original units here because I'm still finding an area. If I was finding an indefinite integral, an antiderivative, and there was no limits of integration there, I need to go back in my original units. But here, I just have to find the number. Sometimes those limits of integration that you get in the new problem are easier. Sometimes they're not, but it's still the same thing. So that's our quick excursion on U substitution. Again, if you have any issues, okay, with understanding the principles behind U substitution, I highly encourage you to go back and rewatch the U substitution video series and also work some of those exercises in the textbook or any that you see online. Well, that's it for the basic integration technique. We're going to come back to this a lot throughout the course. And now let's get into the rest of the topics. I'll see you in the next one.